All right, in this video, we are going to talk about wave particle duality in the context of the electron diffraction. Now, electron diffraction happens in an electron diffraction tube, funnily enough. So an electron diffraction tube is basically just a piece of material at the beginning of the tube with high-speed electrons fired at it, and the result of that is a diffraction pattern created. Now, you've seen electron diffraction patterns, or diffraction patterns before, because you studied, or you will have studied diffraction gratings. So in a diffraction grating, so just to remind you what a diffraction grating looks like, it's all those tiny little slits. We usually fire a laser of an unknown wavelength at the diffraction grating, which then has a screen that's set distance away, and we create a diffraction pattern. Okay, and we end up using the equation n lambda equals d sine theta, with the intention of finding out lambda, where d is the separation between the slit separations on here, and theta is the angle from the middle line to the order that we're interested in case in this picture, the first order. You could obviously have a second order as well on either side, and your value of n would be 2 in this case here. But we're not looking for the wavelength anymore, and actually we get a very different diffraction pattern here than as we would have done here, because normally you observe these as almost like little spots on a screen. What we do observe, however, is kind of something that looks like this. It's like concentric circles. So we have this central maxima, the same way we do here, and then we have these circles on this screen here, represented by these points here and here. And here, because obviously you might have two sets. And in the same way, these are orders of magnitude, with this is your first order and this is your second order. This is your first order, this is your second order. Now the difference is this diffraction pattern is a circle instead of spots as we had up here. Well, hopefully that shouldn't be too hard to accept, because the nuclei in a material are arranged very similarly to that, in rows or in layers, and we get a diffraction pattern around, because the electrons can travel anywhere around those, so it makes sense that we have a circular diffraction pattern rather than the spots that you get from all the lines over here. So we can use the same equation. The same equation can be used to work out the wavelength, but actually we're doing this the wrong way around, because the whole point of this experiment isn't to work out the wavelength. It's to work out what the nuclear spacing is of the nuclei inside of whatever material that you've got placed here. So you're trying to find D, effectively. So we rearrange this equation to find D. Theta can be obtained exactly the same way as before. That would be theta there. You could do some trigonometry to work out what this angle is if you know certain distances on this electron tube, not too much difficulty. And as a result of that, what we get is we can find D. But the problem is we don't know what lambda is. We need lambda to work out what D is. Well, we come to the part of this video where we talk about the wave-particle duality equation, I like to call it, or the de Broglie. So de Broglie is a French name, and he came up with the equation lambda equals h over mv. Now, this equation should only be used when talking about particles acting as waves, okay? So, as a result of that, notice that the particle part of this equation is the m. The m is mass, so that denotes something that is a particle. The lambda is a wavelength. That's something that's behaving as a wave. And so what the Debris wavelength is this value right here. It's the wavelength at which a particle displays wave behavior. Okay, so it's displaying wave-like behavior. And as a result of this equation, hopefully you can see here that we can obtain the wavelength as long as we know the mass of an electron and the velocity of an electron as well. Well, the velocity is pretty easy to obtain of the electron. If you're not sure how you would get that, recommend go back and watching my electron gun video, because this is actually the same principle. So you can get the velocity from knowing the voltage at which you've accelerated these electrons. So once we have the velocity, we know the mass of an electron. This is Planck's constant. We can work out the Debris wavelength. At that point, it's as simple as rearranging this equation for d. So we have n lambda over sine theta equals d. And that allows us to work out what the separation of these nuclei is, or the approximate size of them, as we have right here, which is pretty cool when you think about it, because that allows us to kind of know more about what's going on with atomic structure. And this is one of the ways that we can do that. So this equation over here, the Debris equation, we'll be using in class, as well as maybe, depending on your specification, you may see contextual questions that involve this equation from previous learning. So the idea being is that the prime focus is this. Now, there are some variations on this when we can look at momentum, but we can do those in class, and we can actually see what kinds of variations can come up. Also is very interesting is the fact that this equation can be applied to anything that is moving. Anything that has mass and a velocity would technically have a wavelength. You walking or running have a wavelength. Now, what's interesting about that, and hopefully you'll have an awareness about the rules that apply to diffraction very specifically, which only allow diffraction to occur if the wavelength is close to the size of the object being diffracted, or the gap being diffracted through or around. So in this case, we're going to talk about wavelengths of particles, or even a person, when moving, and when we would observe particles to exhibit wave-like behavior. So please come to lesson with your questions ready. You may have many questions about this, you may have no questions about it, but we'll put that to the test, and we'll see if you can apply some of your understanding about what this represents, okay, in different scenarios.